Welcome, guys. Welcome to our day ninth lecture based on hyperparameter tuning. This is your education Suyash, and we are completing our deep learning playlist. In this lecture, we'll be looking at hyperparameter tuning, and we'll be covering random search and grid search. And This is our basically today's plan of action. And today also, as said in the last lecture, that we will not be covering code because we have planned it to cover in the day 10th lecture where we will be doing a complete neural network training. So what we usually do, we first revise what we have done till in the last lecture. We completed regularization techniques, so we have looked on how to basically apply regularization on our overfitted model. So we have already covered that how dropout works, how early stopping works, how L182 regularization works, and how there are basically the techniques to avoid overfitting. So in today's lecture, we'll be looking in hyperparameter tuning and let's just go through the definitions and then just try to go deeper into it by reading the more formal definition. So, types of parameters in machine learning. In machine learning, there are two fundamental types of parameters that govern model behavior. So there are two types of fundamental parameters like model parameter and hyperparameters. So basically, if I just read the definition, you will understand it automatically that the model parameters are the internal variables of machine learning or deep learning model that are learned automatically from the training data during the training process. So what are the parameters you know which are learned during the training? These parameters are like weights and bias. So here again we can look at the example like in weight in neural networks, weights determine the strength of connections between neurons. So it's definition of it basically. But what are the parameters as you have studied? You have completed artificial neural network. You already understand that weights and biases are the parameters which are learned during the training. And if you would have studied CNS, then I would have told you that convolutional filters and NLP embedding vectors are these are the model parameters which are learned during the training. So the definition says this only that model parameters are learned automatically from the training data during the training process. These parameters defines the model's knowledge and are adjusted to minimize the loss function. The back propagation and forward propagation and back propagation algorithm, you learn how that basically we want to minimize our losses so that our model perfectly fits or our model is trained in such a way that we predict more good results. So this is basically the model parameters definition, and the characteristics of these model parameters are that they are learned during training, updated automatically through optimization algorithms, represent the model's learned knowledge, and values are determined by the data. So basically, you got the idea what are model parameters. And hyperparameters are like hyperparameters are the parameters which we configure. So like if I say like we pass these parameters when in the start of training, like the number of epochs, the learning rate, the weight decay, like in L2 regularization, you already seen. So basically, the hyperparameters are external configuration settings that control the learning process and model architecture. These are set before training begins and cannot be learned from the data. They govern how the model learns and its structural properties. So hyperparameters are like we can say like these are one second. These are external parameters which we fixed right now. One second. So hyperparameters are basically the external parameters that we can say. These are external parameters. One second. So basically these are external parameters, and the model parameters are internal parameters which are basically are we get after training like we basically initialize like weights and biases some certain value and then they are trained. So on after the training we get the correct weights and biases. So we basically say that model parameters are we first fix them or try to randomly initialize them, and then they are finally trained, and then we get the final model parameters. In hyperparameters, they are external parameters which we provide before or configure in the settings before training process. So the characteristics of hyperparameters are set before training begins, not learned from the data. Control the training process and model architecture. You already know you have already seen in the visualizer. Like we can also say that different types of optimizers like RMS prop or SUD or ADAM. These are also hyperparameters because we configure our architecture to fix these configuration like optimizers. We select a particular optimizer and then the training process takes place with that optimization technique. So basically, we can say that these are also hyperparameters. And you have already seen how these optimizers give different works in certain way to give a certain like maybe for certain epoch SUD is working good for like it will take less number of epochs for like for NEG, and it will take a certain more epochs for like momentum where you already have covered like we are getting the results faster we are getting our results in NAG are faster than momentum, maybe because in momentum it is taking certain time to settle down. Or like you know that ball diagram, like it's falling in a convex function, and it took certain more time for that simple momentum optimization to settle down. And but for NAG, you have already seen that it reduced damping, so it settled down in before certain epochs. So we can say that these are also optimizers, and you can by setting the optimizer, you can control the training process and model architectures and it requires manual training or automated optimization and affect how model parameters are learned. So these are basically hyperparameters also affect how model parameters are learned. You can already think of it like you can just imagine how these can affect the model parameters. Like you already have seen that weight ablation rule in different optimization techniques, and you can see how the model parameters like weights are affected by these hyperparameters. So there are certain examples like learning rate controls how fast the model updates and its parameters. Batch sizes also are hyperparameters, like we fix them before training. And the number of epochs, network architecture also is a hyperparameter, like how many layers in basically how many layers we want in a neural network, and then how many uh, neurons per layer we want. These are hyperparameters. Regularization parameters are also hyperparameters. So basically, these are the difference between model parameter and hyperparameter. So this is there. I also pasted a table like differentiation between like learned from data set manually, automatically. You can just look by the aspect and compare, and timing updated during training, set before training, and for the purposes of stored learn knowledge, control learning process. So this is the good part. Like what is the purpose of model parameters and what is the purpose of hyperparameters? So parameters are stored learned knowledges, and hyperparameters control learning process because they can affect the architecture. They can basically they can affect the architecture if the hyperparameters certain hyperparameter like number of layers worked good for certain data. So these are they can affect the control learning process. They can control the learning process like epochs, like optimizer. You can just also add like we can add a type of optimizer. So basically, if you just try to add one more example like optimizer, so there are different maybe SGD or maybe ADAM or maybe RMS prop. So these are also hyperparameters, like they affect the uh, learning process. And example are weights and biases, and here example are learning rate, batch size, optimization, gradient descent, and grid search and random search. So basically, uh, in model parameters, I think this optimization thing is not exactly correct about it because in hyperparameter, grid search and random search are the methods which we use. to get a correct to get up those certain parameters of hyperparameters so that the losses basically we optimize our training process. By optimizing our training process, we mean that by getting certain such model parameters which predict for the testing data better. Basically, we want to minimize the losses. So we select that hyperparameters using grid search or random search or maybe Bayesian optimization, those certain parameters, those values of those certain parameters, which basically helps in training our model in such a way that we get a perfect, we can say close to perfect model, where our model the losses are less, so that the model predicts correctly. So this isn't exactly correct about like optimization. So you can just cut this out and you can just remember that for these are basically the aspects, and for optimization it doesn't mean that it we are using gradient descent because maybe we are, yeah, gradient descent is the basic one, but the optimization techniques you already covered. There are basically many optimization techniques which are worked on gradient descent, or we can say which are worked with gradient descent, like certain parameters are added to the gradient descent formula. So basically you can say that it is not exactly correct about it, but and like grid search and random search are methods which we can say that we deploy to get the best hyperparameter values for different hyperparameters like basically the learning rate, batch size, the correct value or the value which provides a better result for our model so that it can fit properly in training data and also work like in good way in testing data. What I mean by in good way that it doesn't overfit or underfit. It gives a very balanced result. Like for validation, the validation accuracy and testing accuracy are close enough. So we can say that our model is not overfitting and it is balanced. So, what is hyperparameter tuning in deep learning? Hyperparameter tuning is the process of selecting the best set of hyperparameters for a machine learning model. Hyperparameters are different from model parameters like weights and biases, as they are set before training the model and cannot be learned from the data. Examples of hyperparameters include learning rate, batch size, the number of epochs, optimizer choice. Yeah, they added here optimizer choice and network architecture details like the number of layers or neurons per layer. So basically, by the definition, I already explained these things. So the definition also speaks the same thing. And effective hyperparameter tuning can significantly improve the model's performance, often making the difference between an underperforming model and a high accurate one. So and a highly accurate one. So basically, with the correct parameters, hyperparameters which are tuned, or choosing a certain hyperparameters like controlling the learning rate and either scheduling the learning rate or any correct number of hidden layers like correct neural network architecture. There is basically not the correct thing, but which I can say that the best thing which is suited for our data. You can make a lot number of layers, but it will be unnecessarily if it is not giving a good training and testing accuracy. So we are selecting a certain number of layers which best fits to our training, fits to our test training and testing data. So that is why hyperparameter tuning becomes significant. So what are hyperparameters? You already have looked at hyperparameters. So the definition, I think it is something is repeated here, like you already have seen hyperparameters and model parameters. So common hyperparameters in deep learning, you already have seen. Dropout rate is also a hyperparameter you can see because we already fixed that how many percent the dropout ratio we apply for a particular hidden layer, how many we want, how many percent of neurons to be deactivated for a certain for that epoch. Basically, we fix the dropout rate or dropout ratio P, which we take. You already know about dropout rate. We have studied this in last lecture of regularization. So there are several techniques for tuning hyperparameters. So like grid search and random search. Basically, we will be covering these both uh, in this lecture. So grid search is an exhaustive search method where you define a grid of hyperparameter values and a model is trained and evaluated for every possible combination. It's a brute force approach that evaluates all possible hyperparameter combinations and picks the one that performs best on validation set. So basically, we are training a model. So if I say that if we are considering the only maybe if I just go here, yeah. So let's just consider hyperparameter 2 and hyperparameter 1. So let's just suppose that in this hyperparameter it is like if I zoom it, uh, if I say that we are only considering we have fixed our model architecture, we are not changing the hidden layers. We have fixed our optimizer, like consider Adam like optimizer. We are not hyperparameter tuning that like we are not giving it a choice to select our model a choice to select which optimizer best suits or how many number of layers or how many neurons in that particular layer is helpful. We are just tuning our two parameters. Like let's just suppose we are tuning with epoch, and in that hyperparameter one, let's just say we are tuning with learning rate. So what's happening in grid search is that we are manually like getting like number of epochs. If I just say that there are 100, then 200 and 300. So we have just like ABC for learning rate if hyperparameter one. So we can just say that like here the learning rate is 10 to the power minus 3, 10 to the power minus 2, and 10 to the power minus 1. So let's just say that A is 10 to the power minus 3 and B 10 to the power minus 2 and 10 to the power minus 1. So basically what we are doing. And in XYZ we can say let's just say 200, 100, 200 and 300. So this is a list basically where we can say that what our model will do. So we will be making two-dimensional matrix where we can say that for epoch and for learning rate because two-dimensional because we are considering two hyperparameters like which are epoch and learning rate. If suppose let's suppose we add another optimizer another basically hyperparameter like optimizer, then again this 2D will turn to 3D, and then suppose we also add a dropout also as a hyperparameter, then 4D. I hope you are just getting what I want to say, like why we took epoch and learning rate because it's good, it's easy to visualize to grid search in two dimension. We can just change like here if I just cut the epoch and just write a dropout or maybe the number of hidden layers. It's just upon you, but it is easy to teach in 2D. So we are taking two hyperparameters like epoch and learning rate. We can also understand like by if we introduce another hyperparameter dropout or optimizer. So it will just there will be a 3D and in z-axis in z-axis you can see we can say this will be like optimizer. You optimizer or anything dropout ratio or hidden layer or anything like weight decay maybe lambda that you create. So in z-axis I am considering optimizer. So what will happen? So it will happen that we will consider three types of optimizer like SGD or SGD, RMS drop or any three basically. So there will be maybe SGD and then yeah. So basically what is the we can say that how many number of entries in it. So 3 into 3 for the list of three for learning rate types like 10 to the power minus 3 or 10 to the power minus 2 10 to the power minus 1, and then 3 for number of epochs on which we are grid searching, and then we have 3. So it's 27. So what will happen that there are 27 values and 27 basically entries, and our model for in grid search our model will manually use a brute force technique will go here, and suppose then in X we have 10 to the power, basically 100, and then for a 10 to the power minus 3, and for like here it is, if I say for here are entries add, and then it will go for next here, and basically it will also transfers to every data points and will run a model and check on validation data. And if the validation accuracy or validation losses are minimum, that will be our best hyperparameters. So let's just remove that access thing and explain it once more. So suppose what will happen. So how many entries we have now? So let's just suppose for in a 2D case only. So we have like we have set a barrier like our model will select the number of epochs in these three cases. We can also like pass in such a way like model may go to 100, 101. So basically we are not doing so much digging up so much. We are just asking our model to either try 100 or 200 or 300. We can try any number. We can give a range like try between 100 and 200, and then it will just increase the number of data entries in this basically in the grid. So we are just giving a list where we are just trying 100 epoch, 200 epoch, and 300 epoch, and similarly we are doing for learning rate. So the number of data is 3 into 3, 9. So our model will test on these basically 9 times, and then model will train for these parameters and then do validation or testing or validation to get the accuracy and losses. And for the best accuracy, or we can say for the minimum loss, are those hyperparameters will be selected. Like let's just suppose for YB. So basically for a value of learning rate 10 to power minus 2 and y 200. So for this, basically for this, our validation or testing accuracy is best and losses are the least. So we can say that these hyperparameters are good. Basically, these parameters for these values of these hyperparameters are best for our model. So what happens in research, like it just goes to every these target values, and then just like it will go for nine go for each data point in this grid. If it is 3D, then it will go for like if we said like we took three types of optimizers, so it would have gone for 27. And similarly, it will go for every data point in 4D case, then it will also go for every data for that dimension also along with other three dimensions to get the best to test and to train and test, and then for the best results, it will select that values of those hyperparameters. But what happens in random search? Random search, it takes it randomly. Like if we have given like do a random search for 10 times, then it will select any of these values and then just try to train and test our model. And for the best model testing or validation accuracy and least losses, it will select that values of those hyperparameters. So it is just randomly, like just train and test for like 10 times randomly, and for the best result, it will select the values of those hyperparameters. So basically, this is the difference between grid search and random search. So let's just read it and understand. So grid search is an exhaustive search method where you define a grid of hyperparameter. You just understood what is a grid of hyperparameter values. Like in 2D, we have taken two different hyperparameters. We can take a set of two different other, or if you want to hyperparameter tuning of a large number of hyperparameters, then it will be maybe a 5D or in 6D. You got the idea behind it, and you also understand the computational resources which will be exhausted, because every time you are going for a particular set of hyperparameter values and then training and testing, you can get the idea that we are applying a brute force, and how it is very exhaustive, and it is very computationally expensive. So, and the model is trained and evaluated for every possible out combination. Like we took a combination of nine, so basically three into three, so nine. We are training and testing and evaluating for 9 times. So basically, this is brute method. It's a brute force approach that evaluates all possible hyperparameter combination and picks the one that performs best on validation set. So these things I already made it clear by using that figure. So define a grid hyperparameter values for each parameter. Like here they have took learning rate and batch size. We took epochs. So it doesn't matter like they are fixed. They maybe have fixed number of epochs and they are tuning on based on batch size. So this is just an example, and we took a different example. You got the basic idea, I hope. That train the model for all combination of hyperparameters in the grid and select the combination that yields the highest validation accuracy or the lowest validation result. Guarantees the best model hyperparameters within the predefined grid and simple to understand and implement. Computationally expensive. So these are the disadvantages. Computationally expensive, a large number of hyperparameters and values. Inefficient when some hyperparameters are less sensitive to performance. So if certain hyperparameter are less sensitive to performance, then doing hyperparameter tuning with respect to that hyperparameter is useless. So that this is basically the disadvantage. Application best used when hyperparameter such space is small and computation time is not a constraint. So, pardon. So you basically got the idea what it is. It is just written in simple English, and you basically understood what is going on. And random search selects random combination. I already told like you are running a model for 10 times, saying that randomly select some values for these hyperparameters, and the best one is basically your back values of those hyperparameters. Basically, random search doesn't assure. Basically, you can see that it doesn't assure to get the correct or maybe the best values for those hyperparameters. But in grid search, you are assured that you will for after you don't have if time constraint you know that you will get a the certain values of hyperparameters which are best. But in random search, it is really very hard, or it's a random possibility of getting the best hyperparameter value. So you cannot say that the random searches will definitely give you the best results. So from the predefined searches, unlike grid search, it does not evaluate every possible combination, but randomly samples from the distribution. Define a range or distribution for each hyperparameter. So these are the steps. Randomly sample hyperparameter values from these distributions. Train and evaluate the model on subset of these combinations. Same thing which I told you. Advantages you already know because you are not training and testing for the a lot number of times. You are just training and testing for certain times randomly, so less computationally expensive and more efficient when only a small number of hyperparameters significantly affects performance. Can outperform grid search when only a few combination are optimal. So basically for certain hyperparameter, maybe the accuracy is highly dependent as compared to certain other hyperparameters. So it may happen that because of random search, we have found certain combinations which are more optimal. So these were the advantages, and what are disadvantages? That it does not guarantee finding the absolute best combination, which I already told you. Application useful when there are too many hyperparameters to explore exhaustively, and can explore large hyperparameter spaces quickly. So these are the basically the used hyperparameter tuning techniques on methods. So the other method which we have written optional that won't teach you much about it, but there is just a definition about Bayesian optimization. There is a hidden mathematics behind it, which I think it is it is not in our scope of these lectures. So Bayesian optimization, this is a more sophisticated approach for hyperparameter tuning. Instead of randomly sampling hyperparameter combinations, Bayesian optimization builds a probabilistic model of objective function and uses it to select the most promising hyperparameters to evaluate. So there are different libraries which we will be using like Optuna or Hyperrot or Bayesian optimization for doing Bayesian optimization. So basically, we will be using Bayesian optimization for hyperparameter, but the hidden maths which is lying We won't be covering those the hidden behind the scene mathematics. So we will be using libraries for this, and the use case which I try will which will I try. It basically I will try to show you maybe in later lectures, like using Optina or maybe Bayesian optimization or hyperrod libraries. So advantage is efficient for high dimensional hyperparameter spaces require fewer iteration to find optimal hyperparameters. So basically, the Bayesian optimization it considers that the losses are also dependent on different hyperparameters, and it just try to find that basically creates a function. It considers it consider the testing losses to be dependent on to be a function of hyperparameters. So you can see that these hyperparameters are affecting the testing accuracy and losses. So basically, it tries to make a it tries to create a relation between these hyperparameters, uh, which gives basically which results in the best model where losses are minimum. So this will create a function or relation between them, and then it just try to get the optimal value for it. So this is basically the Bayesian optimization thing, which is working in behind. Basically, it is trying to create a function which gives the best optimal results. So this is basically the Bayesian optimization and the key hyperparameters and their impact on models. So learning rate, you already understood what is it. So if learning rate is too high, the model may overshoot the minimum loss, causing instability and failure to converge. So basically, if learning rate is too high, you can just go to the visualization tool and you can see that if learning rate is too high, then it may happen that it may pass that minimum point and may go this way and don't converge, or it may take time to converge. But if it is too low, then it may happen that like subtracting, like you remember the gradient, weight updation rule W nu minus W o, W nu is equal to W old minus neta, and then the gradient with respect to that weight. So if learning rate neta is very small, then it may happen that weight updation may take a lot of time, and you are just stuck in some local minima and you're not getting out. So the typical ranges are in this between this. And this is basically the TensorFlow code. We'll be working on TensorFlow also. Uh, we planned it like if I just go here, a deep dive into TensorFlow docs. So basically we'll be looking at TensorFlow and PyTorch also. So you don't need to worry. You just try to understand the concepts here, and we will be covering those things also in later lectures. So there's no need to worry. Batch size also you can see that's for small batch size. I already showed you if you remember that if we are using uh, basically, if you remember that in small batch there are noisy updates. I already had showed you like in batch gradient descent and stochastic gradient descent. You can see that weight updation is noisy because you are passing every data points and then weight updation is happening and you can see the noise. If you remember that diagram thing, so you would understand this batch size dependency and number of epochs also. The model underfits if there are too few epochs and model just overfits or it memorizes the training data leading to overfitting. So that's why we apply early stop. Early stopping is a regularization technique where training stops automatically when performance on validation data deteriorates, even if the training error is still decreasing. So basically, we stop that training, so we avoid overfitting. So we stop the training when the validation data deteriorates. So validation training accuracy or loss deteriorates. And we also use learning rate schedules like step decay, reduces the learning rate up by a factor of set of numbers of epochs. So after certain number of epochs, we just try to uh, reduce the learning rate, and so the learning rate decreases exponentially during the training. Where exponential decay, we had applied exponential decay. So these things we will be looking in the next coding lecture. So that will also help you understand it. Uh, in a good way. And these basically learning rate schedules, and these are not a topic of theory, but the topic of theory was the idea behind the random search and grid search. So we have already covered it in detail, and other things we will be looking in the code lecture. So you can just read the conclusion of it, like hyperparameter tuning is essential to extract the best performance from your neutral network modules. So you can just read it, and it's the same thing which I've already covered. So in the next lecture, which will be a big one, we will be covering the code part of the things which we have covered. So it will be day 10 lecture, and we'll be covering everything till from day 1 to day 10, and maybe some things which will be taught in future, but will be covered in those in that lecture. And theory behind it, the idea behind will be taught maybe in certain in next lecture only, in the next to next lecture of it. So you don't have to worry about it. So let's just wrap it today's lecture. Thank you.